Good morning. Welcome you all to this Radiation Oncology Physics course, and this is the lecture number 10, and today we are going to discuss about the rest and last part of the measurement of ionizing radiation, and this is the part 3, and I hope that you are getting some essence of radiation oncology physics in our past 9 lectures, and today I am going to complete the topic measurement of ionizing radiations. Now, learning objective of this class. In this class we will discuss, in the last class we have discussed about how the measurement of exposure was done and how the measurement of exposure was performed, and this lecture we will discuss the measurement of absorbed dose, and there are certain theory that is known as Bragg-Gray cavity theory we will discuss a little about, and we will discuss various other kind of ionizing radiation measurement system. They are calorimetry, and which is based on the heat energy absorption and the absorbed energy converted to the heat, and this is the calorimetry. And next one is chemical dosimetry, where we will discuss the chemical changes effect, which is directly proportional to the amount of incident radiation, and we will discuss some solid state devices and specially thermoluminescent dosimetry, that is TLD measurement system, and we will discuss the film dosimetry, under which there are two types of film, and they are radiographic film and radiochromic film. As we have discussed that how to measure the exposure in air, but we need to have information what is the absorbed dose, means the energy imparted to the medium. Here medium is air, so how we convert the result of or meter reading of ionization chamber in terms of Ranshan or milliranjan to the or coulomb per kg to the absorbed dose in air, and so this is the absorbed dose calculation in air from exposure. And this is there is some condition we have discussed about the electronic equilibrium, where the system should have same amount of ionization gain and same amount of ionization loss, so we can accurately calculate the energy or charge produced by a particular volume. So the electronic equilibrium condition must be there, and this measurement is limited up to 3 mega electron volt of photon energy. Before after this beyond this 3 mega electron photon energy, there is a need of huge amount of air, so to make to create the electronic equilibrium. So this is this measurement is limited up to 3 mega electron volt photon energy, and we know that mean energy required to create one ion pair, we can say this is W, is equal to 3.97 electron volt, and this is the energy required to create one ion pair. And we know that electronic charge E equal to 1.602 10 to the power minus 19 coulomb. Now 1 electron volt is equal to 1.602 into 10 to the power 19 joule. So the average energy required per unit charge, W by E, this is the average energy required per unit charge, is 33.997 joule per coulomb. This is the value of average energy required per unit charge. As we want to convert this charge, what is the amount of energy absorbed to create this ion pair, this is we are going to calculate. So dose in air, this is dose is air, means exposure in Ranshan, and W by E is the average energy required per unit charge. So dose in air, if it is expressed in terms of radiation absorbed dose rad, so this is 0.876 this is actually rad to Ranjan to rad conversion factor and multiplied by exposure in the unit of Ranjan. So XR is the exposure at any point, and this is 0.876 is the rad to Ranjan conversion factor. By this formula we can convert the exposure to the dose to the air, and we have already limited this measurement. This is there is electronic equilibrium must be there, and it is limited up to 3 mega electron volt photon energy. Now, as this condition that in the earlier calculation we use that there must be electronic equilibrium, and this is limited up to the photon energy, and this calculation is only for air measurement and only for X and gamma photons, only for X and gamma radiation. But in our practical radiation oncology, we treat patients, they are not, they are actually medium like soft tissue, bones and other tissue materials. So we need to convert, we need to calculate or devise some methods by which we can calculate or we can measure the dose to the to any tissue or any point. We can calculate the dose in water or any other medium than air. So Bragg-Gray cavity theory is a huge, it's a very vast topic, but here I have limitation of time. So I am just going to elaborate some basic fundamentals or regarding the Bragg-Gray cavity theory, and this theory actually eliminates the above restrictions. Here the ionization produced in a small gas filled cavity placed in a medium. This is our measurement system by ionization chamber, and we have to assume that this ionization is related to the energy absorbed in surrounding mediums, and introduction of small cavity does not alter the distribution of the secondary charge particle or secondary electrons. Means there is no, as this gas filled cavity is very small, so we can eliminate these contributions that there is any change of distribution of secondary electrons. So we just consider, or we can just assume that introduction of small cavity does not alter the distribution of secondary charge electrons. And by these assumptions, the Bragg-Gray relationship is dose in any medium, it may be soft tissue, it may be water, it may be bone, that Jg, I am going to explain, Jg multiplied by W by E, this is the average energy ionization, this is the average energy absorbed per unit mass of the cavity, and D medium is the absorbed dose in medium without cavity. This is the dose, and we just neglecting the cavity, we just consider that it is a uniform medium. And Jg is the ionization charge of one sign produced per unit mass of cavity gas. Jg is the ionization charge of one sign, it may be plus or it may be minus, per unit mass of cavity. And S by P, S by rho G to medium is the average ratio of mass stopping power, because we are considering the electron secondary charge particle. So we are going to use the interaction quantity as a mass stopping power, and here we are taking that average ratio of mass stopping power of medium, the medium where we want to calculate, where we want to measure, to that of the stopping power of the gas. And Jg multiplied by W by E is the energy absorbed per unit mass of the cavity gas. This is the energy absorbed per unit mass of the cavity gas. So this is all about Bragg-Gray cavity theory, and as I have already told you that this is a huge topic, and because of limitation of time, I am not able to discuss all other theoretical and basic formulations of Bragg-Gray cavity theory. There are some international codes or protocols which are used for measurement, which we are using for measurement of our therapeutic units and patient dose measurements. These are some there are some international codes which are widely used. First one is Technical Report Series. This is by International Atomic Energy Agency, IAEA, and they have various kinds of technical report series. The photon dose or gamma or X-ray dose calculation protocol, they formulated or they given the code TRS 277 and TRS 398. These are two reports which are given by International Atomic Energy Agency, IAEA. And next one is Task Group Report. They are TG reports, and they are from American Association of Physicists in Medicine, AAPM, and they have given the similar kind of, almost similar, they have some differences, TG21 and TG51. These are two task group reports which are used to calculate the absorbed dose in medium. If any medical physics personnel is going through this our course, so they should read all these technical report series for their professional purpose. Now coming to the different kind of dose measurement, other kind of dose measurement system than the ionization effect. First one is heat effect based calorimetry, and here we know that we have already mentioned that energy is absorbed by medium from the incident radiation, and this absorbed energy may be converted to a minute amount of heat, and if the heat is increased, so there is a increment in the temperature. So if we able to measure the small increment or minute increment of the temperature, we can measure the absorbed dose, the amount of energy received by the medium. So principle is absorbed dose from radiations is converted to the heat energy, very small amount of heat energy, which increase in temperature of the medium. And here is this is a Domains calorimeter. This is used for the primary standard for dose measurement, and here in this Domains calorimeter, this is a famous calorimetry system where there is a water in the glass jar, and this glass jar is, this volume of water is isolated, thermally isolated from the remainder rest of the world. So there is no heat loss or heat gain from outside to this medium of the water, and there is a polyethylene film, and we use a bead thermistor. This is a bead thermistor. This is very accurate in measurement of temperature, and here is a polystyrene ring which is used here, and this is accurate. This bead thermistor is accurately measure the temperature. So by measuring the temperature, we can directly calculate the absorbed dose by the of the radiation. So by formulation that we know that 1 Gray is equal to 1 joule dot kg inverse, mean 1 joule per kg. That is, the 1 joule energy is absorbed in 1 kg, that is 1 Gray of radiations. So 1 joule, if we convert, this is 1 by 4.18 calorie and kg inverse. If we convert this joule to the calorie, this is the 4.18 is the mechanical equivalent of the heat, means 4.18 joule of energy is equal to 1 calorie of heat. This is the mechanical equivalent of heat, and specific heat of the water is 1 calorie per gram per degree centigrade, means 1 calorie absorbed in 1 gram of water increase the 1 degree of temperature, 1 degree centigrade of temperature. Now, if we convert this calorie per gram per degree centigrade to the calorie per kg per degree centigrade, that this is 10 to the power 3 calorie per kg per degree centigrade. So, the increase in temperature dt by absorption of 1 gray radiation dose, dt is the temperature increment or by absorption of 1 gray radiation dose. Now, 1 gray is converted to the heat, this is the amount of heat, and this is the amount of degree centigrade increment per calorie multiplied by kg. So, this is the formula by which we can calculate the temperature. Here by 1 gray of radiation dose increase the temperature 2.39 into 10 to the power minus 4 degrees centigrade. So, you can see that this is a very minute increment of temperature which needs to be accurately measured by the thermistor. So, this is all about calorimetry. Now, chemical dosimetry. In chemical dosimetry, we use the chemical changes by absorption of radiation, that is chemical effect. So, absorbed dose from ionizing radiation may produce chemical change, and if this change is detectable, the measure of amount, and this is actually the measure of this detectable chemical change is the measure of amount of absorbed radiation dose. So, there are many type of such chemical dosimetry used worldwide, but commonly and most routinely and very easily someone use, that is known as freaky dosimeter, and this is one type of chemical dosimetry and most commonly used dosimetry, that is freaky dosimeter, where ferrous sulfate is we use a solution, and this solution is composed of ferrous 1 micromole of per liter of ferrous sulfate, 1 micromole per liter of NaCl and 0.4 mole per liter of sulfuric acid. This is the solution we used for freaky dosimeter. Now, in when this solution is exposed to the radiation, there is a oxidation. And by which ferrous ions Fe2 plus is converted to Fe3 plus ferric ions. Means after exposing of radiation, there is a changes of there is oxidation and ferrous ions converted to the ferric ions, means Fe2 plus converted to the Fe3 plus. Now, ferric ions concentration is ferric ion concentration can be measured. Ferric ion concentration can be measured by spectrophotometry of exposed solution. If we performed a spectrophotometry study of the exposed solution, we can accurately measure the ferric ion concentration, and by which we can calculate the dose of the amount of absorbed dose of the radiation to this solution. Now, one important type of dose measurement system, that is based on solid state effect, and this is thermoluminescent dosimetry, that is TLD, and dose measurement system. There are various type of solid state devices are available for measurement of ionizing radiations. We use two types of solid state effect based dose measurement system. First one is integrating type and second one is electrical conductivity type, and the commonly used system is thermoluminescence dosimeter TLD. Now, thermoluminescence, there are such some crystals, thermoluminescence are such crystals which after irradiation, if we irradiate such type of crystals, a minute fraction of energy absorbed in the crystal lattice, and this energy is released on heating as visible photons, and this is known as TL signal. So these photons are TL photons are captured by photomultiplier tube, PMT, that is photomultiplier tube, and this TL output is proportional to the amount of radiation. So this is the way how we measure the radiation. So in thermoluminescence, if we have a sequence that some crystals which having the thermoluminescence property, and what is the thermoluminescence property? Such if these type of crystals are irradiated, there are minute fraction of energy is absorbed in the crystal lattice, and this energy is released on heating. If we heat the exposed crystal, then we will get visible photons, that is TL signal, and these TL photons are captured by photomultiplier tube, and TL output is proportional to the amount of radiations, and by which this TL output, from this TL output we can measure the amount of radiation absorbed by this crystal. Now I am going to discuss the physics behind the thermoluminescence. There are if we know that there are two bands, one is valence band and another is conduction band, and in between valence band and conduction band there is a forbidden gap. But if we dope or if we contaminate, if we dope some metric crystal with some other type of elements, there are some electron traps are created in the forbidden gap, and this is the crystals which shows the thermoluminescence property. Now if thermoluminescence crystal is exposed to the radiations, what happened? The valence band electron is received energy and it moves to the conduction band. And some of these electrons will come to the valence band, and some of electron will trapped in the electron traps which are in the forbidden band. So when we heat the exposed thermoluminescence crystal, what happened? That these electrons again goes to the conduction band, and this conduction, from this conduction band they are coming down to the valence band, and they will give some photons. They are known as TL photons, thermoluminescence photons, and this is the amount of photons which is proportional to the amount of absorbed dose. So in this phenomenon we have explained the physics behind the thermoluminescence dosimeter. Means there is a valence band and conduction band. After exposing the radiation, some electrons goes to the conduction band. If the radiation is high, this number of electron goes to the conduction band is proportional to the radiations, and the number of electrons trapped in the electron traps is directly proportional to the radiations, and the number of electrons coming down to the valence band while heating is directly proportional to the radiations, and the amount of TL photons is then proportional to the radiation. And this is the measurement system, actual measurement system, where while we read the thermoluminescence dosimetry after exposing of some amount of radiations, here we have a heating assembly and we have a plate where we place our TL sample, our TLD samples, and after heating this TL sample gives the TL photons, and this minute amount of photons is received by photomultiplier tube, and after multiplications this gives some electronic signal, and this signal is amplified by amplifier, and this is display in a display system, and this PMT tube is connected to the high voltage supply. So this is actually reading process of the thermoluminescence dosimetry. Now film dosimetry, there is two types of film, one is radiographic and another is radiochromic. In radiographic film there is a transparent film base that is made up of cellulose acetate or polyester resin, and in radiographic film there is a emulsion coating both side. Actually these emulsions are small crystal of silver bromide, small crystal of silver bromide. So in radiographic film there is two part, one is transparent film base and another is emulsion coating both side, and the is made up of cellulose acetate or polyester resin, and emulsion coating is made up of small crystal of silver bromides. Now when we expose the film to the radiation, a chemical changes takes place, means Ag plus and Ag and Br minus. So this Ag-Br is ionized. So Ag plus and Br minus, and this is actually latent image. This affected crystal, the part, which part of radiation, which part of the film is getting affected, is converted as small grains of metallic silver. So there are three post irradiation process. One is development, another is fixing, and another is washing. During the fixing of the development, what happened? This metallic silver part, the conversion of metallic silver Ag-Br to metallic silver is increased a little bit, means it's amplify the radiation effect. And during fixing process, the unaffected granules, which part was unaffected by radiation and not received the certain amount of radiations, they leaving the clear film, and metallic silver is not affected by the fixer, it is stayed there only, and it caused the blackening of the film. So degree of blackening is measured by determining of optical density. There is a term, this is known as optical density. Now what is optical density? This is the log 10 I0 by IT, where I0 is the amount of light collected without film and IT is the amount of light transmitted through the exposed film. So this is, if we plot the optical density to the dose of a known dose exposure, we will get a calibration curve, and after which we can get any type of unknown radiation of any particular optical density, we will get the dose, what is dose received by the film. So first we need to calibrate the film, and we will able to measure the dose received by the film. And nowadays we are using radiochromic film, which is very commonly used because of their easy to use process. And in this radiochromic film, its contain ultra thin 7 to 23 micron of colorless radiosensitive leuco dye and a thick 100 micrometer of mylar base. And when unexposed, this film is colorless. When exposed, this colorless film changes to the shades of the blue, and radiation because of radiation induced polymerizations, means colorless film converted to the shades of the blue and because of radiation induced polymerizations. The degree of coloring is measured by spectrophotometry. This type of spectrophotometry we have used to identify the ferric ion in the chemical dosimetry system. So what is the advantages? So no physical, chemical or heating post processing is required, and this film is tissue equivalent. In radiographic film we used Ag silver, that is not tissue equivalent, and here high spatial resolution is available, and we have a large dynamic range, means we can measure the dose from 10 to the power minus 2 to 10 to the power 6 gray, and very low energy dependence, which is a ideal character of radiation detectors, and it is insensitive to the visible light. And this is all about the measurement of radiation and of this measurement of ionizing radiation. Thank you all.